Hi, this is Tom, and we're going to continue lesson 19 in this video. And what I've done is I've taken the blue standard normal distribution that we ended with, and I've created a picture here with just that image. Now, when we make this image, we're still using the same, we're still going to use the same ideas that we did when we made this. For example, the mean of the standard, let's do this. The mean of our standard normal distribution is right in the middle. It's exactly in the middle, and that's 0. And as a matter of fact, it's always 0. Now, the next thing is we measure, just like we did up above, we measure the horizontal axis in standard deviations. And so we could go above 1, 2, 3, and we can go below as well. So we go 1, 2, and 3. And so these, if we label the numbers to the right are 1, 2, 3, and you could keep going, but we're going to get to that in a moment. 3 standard deviations above the mean, and we could go -1, -2, and -3 standard deviations below the mean. So on the left, these are standard deviations below the mean. Oops. And on the right, these are standard deviations above the mean. Now also, we call the measuring of our data in standard deviations. These are called, let's do this, these are called z-scores. And we'll understand more why, but for now, any number on the horizontal axis is referred to as a z-scores. So called z-scores, these are the numbers on horizontal axis. Okay. Now, a few more things, and that is this. Notice here that the curve, it never touches the z-axis. I know this is gonna. Now here's a strange idea, and what it does is, and not only that, it gets closer and closer and closer. So imagine this. Imagine that I continued way off to the left, way off to the left. And who knows what numbers these could be? -10 and -11. It doesn't really matter. But if we were to take, say, if we were to take a magnifying glass and zoom in on this area. Here's our magnifying glass. If I was to take that and I was to zoom in, what I would see is a picture that looks like this. The normal curve would be getting closer and closer and closer and closer, but it wouldn't quite get there. No matter how far out we went, if we just kept zooming in, all we're going to see is that picture right there. The picture where the normal curve is just getting closer and closer. Now here is the conundrum, if you've ever had one. That is this, that if you shade all of this, even though it goes forever, if we shade the whole picture, shade the whole picture, it represents 100% of the data. And to prove this is a rather challenging calculus problem, and we don't need to do that, but we do want to get the idea that even though it goes on forever, that is so small that at some point it doesn't actually add any value at all. And so you really can just shade 100% of the picture. Okay. The next thing is this. And we could kind of see it in the picture above, but when you have all this nice smooth curve, it takes on a unique property that's very, very well known, and that is this. If I go a standard deviation below the mean, and I go here at 1 standard deviation above the mean, I'm going to put the mean right, it goes right through the very middle of my picture. And then if I start shading this region, I'll just use some simple lines. You may do a better drawing. But if I shade all of this between -1 and 1 standard deviation, it represents 68% of the data. So that's the number we're going to use. So between -1 and 1 is 68%. Now, this pattern even continues again. Suppose I went to 2 standard deviations. I went 2 below and I go 2 above. And then I do the same thing. I start shading. Well, now, when I am done shading between -2 and 2, I will have then shaded exactly 95% of the data. That's what that picture now represents. Instead of shading bars of a histogram, we're shading regions under the curve, but it's this exact same idea how in a histogram, a bar represented the area, and now the amount we shade represents the area, and it also represents the percentage. I'm sorry, the area that we shade represents the percentage of the data. Now, let's just be so crazy that we go all the way out to 3 standard deviations. So I'm going to go 3 standard deviations below and 3 above, and then start shading. And if I do this, I will have shaded 99.7% of my picture. There's this little tiny space left out in those tails, and they do have values. So we haven't shaded 100, but we've shaded 99.7% of the data. And this pattern is called, the empirical rule. And it says, the empirical rule says that of a normal distribution, %68 of the data is within 1 standard deviation of the mean. And it goes on. It says 95. It's exactly what our picture is. I'm just putting it in words. 95% within 2 standard deviations of the mean. And 99.7% within 3, oops, I should be consistent there, within 3 standard deviations of the mean. And those are the properties of the standard normal distribution. And there's one more, and that is that it's symmetrical. I'm going to put that up here, symmetrical. And it's symmetrical about the mean. And we saw this in the picture above, symmetrical about the mean. And what this means is that if I was to fold my picture right here, right along that line, that vertical line above the mean, that my picture would line, each side would line up exactly perfectly. And that property and the application of the empirical rule is what we're going to do in the next video. Thanks for watching.